So consider the problem of trying to find the derivative of this quantity here. Take the integral from 0 to a sliding limit x squared of the function cosine of t to the fourth power plus 1. In other words, apply d dx to this quantity. And here is a question for you. Do you suppose that this is just equal to cosine of x to the fourth power plus 1? After all, in the previous example, all that we had to do was put x in t's position. Now I'm a little bit dubious about that because the first difference between the example that we have now and the example that we had before is that our function has an upper limit of x squared, whereas before we had an upper limit that was just x. So maybe what we need to do is replace t with x squared. Maybe that is reasonable. But a more fundamental problem is that this replacement process fundamentally was based on this fundamental theorem of calculus. And this fundamental theorem of calculus was only valid in the case that the lower limit was a constant and the upper limit was just x. Therefore, it's completely invalid for us to try and apply the fundamental theorem to this function at all, because this function doesn't have the correct format. Ours has an upper limit of x squared. It's supposed to have an upper limit of x. Now, to get around this problem, what we're going to do is we're going to use chain rule. I'm going to call our function h of x. This is the function that integrates from 0 to x squared cosine t to the fourth power plus 1. I'm going to call f of x the function that we wish we had, which integrates not from 0 to x squared, but which integrates from 0 to just x. If I had this function, f of x, I would be in great shape, because f prime of x can be found just by plugging x into t's position. However, our actual function h has x squared in x's position. In other words, our function h is equal to the composition of x and x squared. If you put x squared in x's position in the function f of x, you will obtain our function h of x. What this means is that we can find the derivative of h of x by using the chain rule, h prime of g of x times g prime of x. F prime of g of x can be found by taking f prime of x and substituting x squared in x's position. But then I need to remember to multiply by the derivative of the inner function, by 2x. And this will be the genuine derivative of the function in this example. So we almost had it on our initial guess. Replace t with x squared. But because of chain rule, we had to replace t with x squared and multiply by the derivative of x squared. So here is an example of how to use chain rule to find the derivative of an integral where the upper limit is not just x.